In this video, we're going to introduce the limit laws that we can use to solve limits algebraically, and then we're going to do some examples. So I'm going to introduce all the laws first, and then we'll use them and compute some limits. So let's let little a, capital A and B be real numbers, and f and g are functions, so that the limit as x goes to a of f of x, little a, I guess, of f of x equals capital A, and the limit as x goes to little a of g of x is capital B. Okay, so these limits exist, okay, and they're equal to a and b, respectively, for f and g. So the first one, if we have a constant k, so k is just a number, and we want to take the limit as x goes to a of k. So we did one similar to this in a previous video. So here, this limit is just k. So this is a constant. So the idea here is if you have a graph and your function here, so I don't want to call it f of x, let's say h of x, okay, it's just k. So that means the graph of it is a horizontal line. So at any point A, okay, you're going to approach k because it's already there on both sides. So the limit of k is k. We also have this constant multiple rule. So if you have a constant, okay, k times a function, you can actually pull the constant outside of the limit. Okay, so here we would have k times the limit as x goes to a of f of x. And because this is equal to a, we can write it as k times capital A. So that's a constant multiple rule. We also have a sum and difference rule. So if you want the limit as x goes to a of a sum or difference of functions, so you're adding or subtracting two functions, you can actually do the limit separately and then add or subtract after. So this is the limit as x goes to a of f of x, plus or minus, okay, whatever it was, the limit of as x goes to a of g of x. Okay, so here that would just be a, capital A, plus or minus capital B. Okay, so you can compute each part separately and then add or subtract the result. Okay, this also works for multiplication. So if you have the limit as x goes to a of f of x times g of x, okay, you can do these separately. So the limit of as x goes to a of f of x, and then multiply by the limit as x goes to a of g of x. Okay, so that's going to be a times b. So you can multiply after. Now remember, this is assuming that a and b exist, so they're real numbers. If one of these limits went to infinity, then we might have a problem. Okay, so you can still apply the rules in those cases, you just have to be a bit more careful. So we'll talk about that later. For division, same idea. So you could write this, so I have the limit as x goes to a of f of x over g of x. So I can do the limit as x goes to a of f of x, and then divide by the limit as x goes to a of g of x. So that's going to be capital A over capital B. Now this is, you can only do this as long as the limit on the bottom, so the limit of g, so your b, is not 0. Because obviously we never want to divide by 0. So we need to be careful that that limit does not go to 0. So if it does, this rule does not apply. So you're going to have to try something else. So because of the product and the sum and difference rules, it's not too hard to show that if you have a polynomial, okay, p of x is a polynomial, and you want to take the limit as x goes to a of p of x, nothing bad will ever happen here. So the limit is actually just p of a. So that's the polynomial evaluated at x equals a. So you can just plug in a, and that's your limit, whatever you get. Now, if you have a real number k, and you want the limit as x goes to a of f of x to the power k, again, you can move the limit around for when functions are nice. So we can bring the limit inside and take the limit first of f of x, so that's going to be a, and then raise it to the power k. Now again, here I've actually written, provided this limit exists. Okay, so we want to be careful because there's some times where this can go wrong. Okay, so I want to give you an example where it won't work. So let's say k is 1/2 and a is, say, -1. Okay, so then -1 to the power 1/2 is like a square root of -1. Okay, so something bad happened. So because this does not exist, then we weren't allowed to bring the limit inside. Okay, so if something bad happens, then this rule won't apply. But assuming that nothing bad happens, you can take the limit inside the power as you wish. The rule 7 here is actually very useful. So you can say that two limits are equal. So the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x if f of x is equal to g of x everywhere that x is not a. Okay, now the reason why this might be useful is when we simplify a rational function, so we factor and then we cancel, remember that I always write as long as x is not this number. Okay, so if we're taking the limit at that number, we can use the simplified version. Okay, so that can be very useful. So now if you have a real number b bigger than 0, probably not 1 as well, but and you want the limit as x goes to a of b to the power f of x, you can actually put the limit in the power. So it's b to the power limit of f of x as x goes to a, which is going to be b to the capital A. Okay, and similarly, we haven't done a lot with logs, but if you have base b, so in order to be an allowable base, it has to be between 0 and 1 or bigger than 1, so positive and not equal to 1 is what that says. And we want the log base b of f of x. What you can do is bring the limit inside the log. X goes to a, not b, of f of x. So that's going to be log base b of capital A. Now, again, nothing bad can happen. So this is assuming that your a is positive. Okay, so if a is negative, you can't take log of a negative number. That's something bad. Okay, so that would be an instance where we could not do that. But basically, as long as nothing bad happens, you can usually do what you want to do when you're using limits. So let's try some examples. So in this first one, I want the limit as x goes to 1 of 3x squared minus 2x plus 4. Now, we could use a variety of rules here, but the one that I want to use, so it's just one rule, this is a polynomial. Okay, so because it's a polynomial, this limit, so let's call it p of x, because it's a polynomial, what we can do is just plug in 1. So that's where the limit x is approaching. So it's just p of 1. So that's going to be 3 times 1 squared minus 2 times 1 plus 4. So that's 3 minus 2 plus 4, which is going to be 5. So here we used the polynomial rule. Okay, you don't have to remember all these names or the numbers of the rules, okay, but for now I'm going to try to refer to them so we know when we're using which rule. Okay, let's try another one. So here we have the limit as x goes to 3, and then we have a fraction here, so x squared minus x minus 1 over the square root of x plus 1. So we're going to hope that we can use the rule, the quotients rule, so the limit rule for quotients. So I'm just going to try and do that and hope nothing bad happens. Okay, so that's where I can do the limit of the top divided by the limit of the bottom. Okay, so right now we used the limit law for quotients. Oops. Okay, so we need this bottom limit to not be 0. Okay, so we're going to want to make sure that it doesn't end up being 0. So when we're doing the top limit, this thing is a polynomial, so we can just plug in 3. So that's going to be 3 squared minus 3 minus 1. Okay, so that's what that top limit equals. And then for the bottom limit, I'm going to rewrite it. So it's x plus 1 to the power 1/2 instead of the square root. Okay, so 9 minus 4 is going to be 5 on the top. And then I'll write the bottom limit again. Okay, so what we used here was the polynomial rule in that step. Okay, now I want to do the limit on the bottom. So remember, I can bring this limit in. So it's going to be the limit as x goes to 3 of x plus 1 to the power 1/2. So the limit can come inside the exponent again as long as nothing bad happens. So when I do that, the inside limit, this is a polynomial, so we can just plug in 3. Okay, so this is going to be 3 plus 1 to the power 1/2. Okay, let me say here. Okay, we can do this provided it exists. Okay, and then so that ends up being 5 over square root of 4. So we get 5 over 2. So the bottom limit was actually 2. Okay, so what that means is, okay, nothing bad. This limit existed because nothing bad happened. And it also means that the bottom limit here also was not 0. Okay, it was actually 2. So nothing bad happened. So all of our limit laws worked. Now I guess in this last step we used the limit law for powers and then the polynomial rule again. Okay, let's try another one. So here I have another fraction. This turns out to be a rational function. Okay, so I want the limit as x goes to 1 of x squared plus 5x minus 6 all over x minus 1. Now, I don't want to use the quotient rule here. Quotient limit rule. So here's an example where it won't work, won't apply. Since if I tried to do the limit of the bottom, so as x goes to 1, x minus 1, okay, this is a polynomial inside, so it's going to be 1 minus 1, which is 0. Okay, so the bottom limit is going to be 0, so that rule doesn't apply. So we need to think of something else to do. So I'm going to try and just simplify the function inside. So I think I can factor the top. So I want two numbers that multiply to give -6, add to give +5. So that's going to be x plus 6 times x minus 1. X minus 1. Now notice if we had plugged in initially, plug in x equals 1, we would have got 1 squared plus 5 times 1 minus 6 over 1 minus 1. We would have got 0 over 0. Okay, when you get 0 over 0, what this means is that you need to do more work. Okay, so we are going to rewrite our function, and here's where that rule 7 comes in. So because I can sort of cancel this, rule 7 says I can say that the limit here is equal to this limit I'm going to write, the limit as x goes to 1 of just x plus 6. Okay, I'm going to call it, actually I'm going to use blue here. I'm going to call it rule 7. Okay, and then so it's since x plus 6 times x minus 1 over x minus 1 equals x plus 6 as long as x is not equal to 1. Okay, so this is where we're taking the limit. Okay, so that's why I can say those two limits have to be equal, because the functions are equal everywhere where we're not 1. And the limit doesn't care what happens at 1. It only cares what happens around 1, so we can use the simplified version. Now we have a polynomial, so we can just plug in the 1. So this limit is going to be 7. So here we use the polynomial rule. Okay, I think I have a couple more to do. I'm going to stop writing the rules quite as much. So in this one, let's just, if I try to plug in x equals 0, because it turns out if you can plug in where your limit is and nothing bad happens, it means that there are rules that you can use that allow you to do that, essentially. So you're using the rules. If I try to plug in 0 here, I'm going to have 1 over 0 plus 1 minus 1 over 0. So that this is 1 minus 1 on the top, so I'm going to get 0 over 0. Okay, so when you see 0 over 0, what you should think is do more work. Okay, we have to do something here. So what I want to do is try to simplify the expression. So this is why we practice this. So how could I simplify this expression, okay, on the inside of the limit? Well, maybe I just want to focus on the top here and put these two terms together. So to do that, I would need a common denominator. So I have 1 over x plus 1, and then I'm going to have minus 1. But I want to make, or 1 over 1, you could think of. Okay, I want to make a common denominator. So I'm going to times this term by x plus 1 over x plus 1. Okay, so then I have the limit as x goes to 0. So now it's going to be 1 over x plus 1 minus x plus 1 over x plus 1. Okay, all over x. So now when I put these together, I have 1 minus x plus 1 over x plus 1, all over x. Now it's useful, remember this was our main, this line here was our division, our main division line. Okay, so now that I have a fraction on the top, I want a fraction on the bottom. So I'm going to have x, I'm going to think about it as x over 1. So far, I have not used any limit laws. All I'm doing is simplifying this expression. Okay, so at each step, I haven't changed anything in my expression. I'm just rewriting it, but I haven't done anything that used the limit law yet. So now I have a fraction over a fraction, so I can flip and multiply. And I'm also going to simplify here the top a bit. So what I mean by that is that the negative has to go into both terms. And then I'm going to have 1 minus 1, so the 1's go away. So I'm actually going to have negative x over x plus 1 times 1 over x, because I have to flip the bottom one and multiply. So if I rewrite this, it's going to be negative x over x times x plus 1. Here's the first time I use a limit law. So I see that I have x over x, and they're multiplying the whole top and the whole bottom. So this equals, right here. Okay, what I'm using is rule 7. Okay, so negative x over x times x plus 1 is equal to negative 1 over x plus 1 as long as x is not 0. Okay, so that's why this rule is useful, because it allows us to cancel like this. So this is going to be the limit as x goes to 0 of negative 1 over x plus 1. And at this point, now we can actually plug in x equals 0, which means that we're using the quotient rule and then the polynomial rules. But we can just plug in now x equals. Our goal the whole time we're simplifying or using limit laws is to eventually be able to plug in, okay, where x is going. Okay, so the 0. So this is going to be negative 1 over 0 plus 1, which is negative 1 over 1, which is negative 1. So this limit is equal to negative 1. Now notice, another thing I want to point out, notice that this limit notation, I kept writing it. I was writing it every single time until here. Okay, what happened at this step is that we plugged in the 0. Okay, so when we're able to do that without anything bad happening, that means that we have computed the limit. Okay, so we've actually evaluated the limit at this step. So we plugged in 0, which means that we're actually evaluating the limit. So that's when the notation goes away. But you have to keep it until that point. Okay, let's try another one. So I have the limit as x goes to 4 of x minus 4 divided by square root of x minus 2. Okay, so if we plugged in x equals 4, we're going to have 4 minus 4 over root of 4 minus 2, 0 over 0. Okay, so we need to do some more work here. So what we're going to do is try to rewrite this. So simplify this expression. There are different ways to do this. Okay, what I'm going to do is multiply by the conjugate. So I'm going to rationalize the denominator. Okay, so I'm going to multiply by the conjugate on the bottom, which is going to be square root x plus 2. And whatever I do to the bottom, I have to also do to the top. Now, I'm not going to expand the top out, okay? And this is a bit of forethought on my part, because in order to be able to plug this 4 in, I kind of want this x minus 4 factor to go away. So I'm hoping that I can cancel it. So that means that I want to leave it as a factor on the top, so multiplied everything. So I'm not going to expand the top, but I am going to expand the bottom. Now, this is a difference of squares, so you could just know what it expands as. If you don't, I'll write it out here. So x squared squared, so x squared times x squared, plus 2 root x minus 2 root x, and then it's going to be minus 4. Okay, so the 2 root x and the minus 2 root x, those are a 0. And then the square root of x all squared is just x. So I end up with x minus 4 on the bottom. Okay, again, we haven't done any limit laws. All we've done is pre-calculus, just simplifying the expression. So we rationalize the denominator. So notice that there's no more square roots down here. Okay, now the nice thing about this is, look, we have x minus 4 over x minus 4. those things go away. And now using rule 7, so here's where we're using the limit law. I know that this limit that we had in our last step is equal to the limit as x goes to 4 of square root of x plus 2. Okay, and now I'm able to plug in x equals 4. So I'm going to have root of 4 plus 2. So that's 2 plus 2. So this limit is going to be 4. So when you're trying to evaluate your limits, you should always try to plug in the number, okay, that x is approaching. If nothing bad happens, it means that all these limit laws that I've listed for you worked, and it enables you to be able to just plug in the number eventually. So you reduce it to essentially polynomials with addition and subtraction or powers, etc. So you can just plug in the number. If you obtain 0 over 0, then you want to simplify the expression. Okay, so you need to simplify the expression. So what we do, or some tools that we have to do that, are factoring. Okay, so if you have polynomials, you might want to try and factor them. If you have fractions, sometimes simplifying them with common denominators. Okay, can it work? Or you can just multiply by the common denominator, but use common denominators. And then the last tool that we just used is to multiply by the conjugate. Okay, so if you have square roots involved, this can be a useful tool to remember that you can rationalize, and sometimes this might mean rationalizing the numerator, but you can rationalize, and then that can sometimes help you to be able to compute the limit. So those are just some examples where we use algebra instead of the graph to compute some limits.